Hi, I'm here today to talk about refraction and this term that we call the index of refraction. So the index of refraction is just defined as a ratio. It goes by the letter n and it is equal to the ratio of the speed of light in a vacuum to the speed of light in a material. So light changes speed when it enters certain materials. It slows down a little bit when it enters the air. It slows down more significantly when it enters something like glass, and even more significantly when it enters something like a diamond. So the bigger the index of refraction, the smaller the velocity's got to be, right? If this is small on the bottom, then n is big on the top. So a small n gets you, a small v gets you a bigger index of refraction, meaning something with a bigger index, light is traveling more slowly in. And you can see a table of the indices of refraction on the reference table. So light always slows down when it goes into a material, and you can figure out how much it slows down using that table. You'll see the table has a very specific frequency of yellow light associated with it. I can't remember what it is off the top of my head. We'll mention it in class, but when you see that number, that should be a sign to you that you're probably dealing with something on the table for the index of refraction. I don't have a reference table with me right now. Now, just to talk about the term refraction, refraction basically refers to the fact that light, when it passes from one medium into another, it bends, right? And the reason that it bends or its path bends is because it slows down or changes speed. Sometimes it can speed up as well. The only time it won't bend is if that theta I is 0. So imagine, if you will, we're going to look again at our materials. Let's say that this is air and then this is water. And if you get a beam of light traveling like this, and your normal is exactly the same direction, then you're not going to get any bending. It's going to go straight through. And the math is going to show that to us too. But if it does have an angle to it when it hits, boom, and we already saw that you got some of it reflecting off in that direction. We're not really looking at that here. What we are looking at it is how it bends when it goes through. So some of the light reflects, some of the light refracts, and what we can do is again define the normal. And we still have a relationship between what we would call the index of, the angle of incidence. So theta I, if this is our normal, theta I is still defined as an angle compared to the normal. This time though, we're drawing the normal all the way through, and theta R, which in this case is your angle of, last time we said angle of reflection, this time I'm going to say angle of refraction, is defined as compared to the normal also. However, you'll see that the light bends past. So no longer do you have an example where theta I equals theta R. That was only true for reflection. Now we're doing with refraction, so the angle has got to change. Also, just to be clear, when we say refraction, don't get that confused with the term rarefaction that we used for certain types of longitudinal or compression waves. This is light, we're seeing it come in and bounce and hit a surface, and we're going to see what happens to it when it hits that surface. So this gets us to something called Snell's law. And Snell's law is pretty simple. It says n1 sine theta 1 equals n2 sine theta 2. Meaning, if you look at the index of refraction for air, which is about 1, and you look at the index of refraction for water, which is about 1.3, then you can use this relationship to figure out what the angles will be, because you know that n1 sine theta 1 equals n2 sine theta 2. So there's a relationship here, and it makes it really easy to calculate stuff. So let's say, for example, you wanted to calculate a situation where you knew n1 sine theta 1, so it would be like, let's say we knew theta 1 was 45 degrees, for example. So you would say 1, which is the index of refraction of air, times the sine of your angle of incidence, sine 45 degrees, equals n2, which would be 1.3, times the sine of that angle. But we don't know what the sine of the angle is. However, we can calculate it pretty easily. So what I could say would be, if I grab a calculator, sine 45 divided by 1.3 equals sine theta. So theta is going to end up being the inverse sine, -1, of 1 times the sine of 45 all over 1.3. And if I put it into my calculator, I get 45 degrees times the sine of 45. This calculator doesn't have a sine function. See if I can get a better calculator. Okay, here we go. 45 times the sine is 0.707 divided by 1.3 equals the inverse sine of 0.54. And I do an inverse sine of 0.54. And I get 32 degrees. So as long as you know 3 of those things, you can get the 4th. It's pretty easy. You want to make sure you're not in radians, and you just want to be sure that you're careful with the calculator stuff. It's a problem if you get an error message. It could be because you flipped the angles or something like that. Because what you cannot have is a velocity that's bigger than the speed of light, and if you end up getting that, you'll probably get an error function someplace along the way, so you'll flip something. I'm going to erase this right now. There's one other thing I want to get to, which is called total internal reflection, which is related to refraction. So sometimes you don't get refraction. Even if you have like water and air, you only have reflection. And it's a special kind of reflection. It is called, let's see, total internal reflection. And this happens when you get to a specific angle. You end up finding an angle of incidence over what we call the critical angle. And your refraction disappears. And just a simplified way to find this is what you end up getting is I'm going to call it n of 1 sine of your critical angle, theta c, is equal to 1. Meaning if you have material that comes through, and it's only going to work in certain situations, like it won't work when you're going from water to, air to water, but it will work when you're going from water to air. You can get something here where you get reflection but not refraction. There's no refraction whatsoever in your critical angle. So you're going to have like an n of about 1.3 here, and the light comes in. There's your angle of incidence. And you're going to just want to realize that 1.3 times the sine of this is equal to 1. That's the critical angle at which total internal reflection is created. Just like with previous examples, you can also get this stuff happening. It doesn't have to be north and south. It can be east and west. You could have a ray coming in like this, and you would have a reflected angle, and you would have a refracted angle, and you could draw your normal in, and you get your angle of incidence. That is your angle of refraction. That here is your angle of reflection. And typically also you will see if the beam slows down, so it will bend towards the normal. So this would be like faster versus slower, like from air into water, it should bend a little bit closer to the normal. But if light is going slower and moves faster, like it's going from water into air, then it's going slow to fast, you will see that this light bends in the opposite way. It doesn't bend toward the normal, it bends away from the normal. So your theta reflected will be bigger than your theta incident. We'll work through more problems related to this stuff together as a class. If you've got any questions, please don't hesitate to let me know. I know there's a lot out here. But I want to thank you very much for watching.